Good afternoon. Good afternoon, everybody. I am not going to repeat any introduction because most of you were here yesterday. So it's my pleasure again to have here my friend Bjarne Stroustrup for the second day to talk about a very interesting topic. Before going there, a short announcement for those of you that are master or PhD student and will need a attendance certificate. There are sheets over there, so at the end of the talk you come down and you write your name and the program you are registering so that we can make the certificates. Okay? So once more a reminder that for those of you that are interested in C++, I hope most of you, we will have our C++ conference here in this room 27 and 28th of April. So we will be announcing speakers and other things very soon. And after the short advertisements, it's my pleasure to have here again Professor Bjarne Stroustrup. These days he's a true professor because he's now full professor at University of Columbia. So you must add this to this long, outstanding CV. And I will not say anything else because you don't want to hear me, you want to hear Bjarne Stroustrup. So thank you very much.
Hello, thanks for coming. Yesterday I was describing the evolution of C++ up to this day, and so roughly I could describe facts and what had happened. Today I'm going to talk about work in progress, things that might happen, though it is not science fiction. I've been working in this particular area for years, and you could argue decades, so it's not brand new. I'm talking about how to make C++ safe in a particular area of type and resource safety, and I'll talk about that. So basically, this was the idea for C and C++ from the early days. We just couldn't do it. Like Dennis used to say, C is a strongly typed, weakly checked language. This was good enough for major successes and also led to many problems. And these days, in certain areas, we want C++ to be a strongly typed, strongly checked language. And so we have to see what we do, how to do that. And basically, I see the discussions on the web. People are fanatical either way. They want absolute safety in absolute every way, which they can't get. Or they say, well, we can write beautiful code. We don't need any help. Well, being careful isn't good enough, and perfection, as usual, eludes us for absolute perfection. So we want to get a C++ that allows us to express what we want to express as we have been able to do it for years without unnecessary overhead, unnecessary trouble of expressing what we want. There's a paper there, a brief introduction to this model, which is one that I actually wrote 7 years ago, emphasizing my point that we didn't start yesterday. And I'm going to talk a little bit about it. I'm going to dig into some corners. Maybe I waffle in some areas because it's work in progress, but there's a basis to it. Basically, what do I mean? Every object is accessed according to the type with which it was defined. So you don't actually access a device driver as if it was a matrix, or you don't address a a string as if it was an integer. This is obvious. We always do that. But then we go and do things like use unions and get them wrong. We use casts and mess up things and things like that. We have to stop it. We have dangling pointers, other things that can compromise our good program. And every object should be properly constructed and destroyed. We do not want uninitialized data being used. We don't want memory leaks and things like that. If you're writing a space program and you have a memory leak, when the system freezes, you can't send a repairman. So we don't want that kind of stuff. Every pointer either points to a valid object or the null pointer, which means that they don't point into nothing. It doesn't point to a memory that has been deallocated or something like that. And by the way, in a lot of areas we don't want a garbage collector either, because a good copying garbage collector means we need twice as much data space and things like that, and more indirections. Every reference through a pointer is not through a null pointer, and every access through a subscripted pointer is range checked. That must be case, because if we have arrays of variable sizes, we have to check. So we must have some checks somewhere to get absolute guarantees. This happens to be what you can read in KNR 1 in the manual. This is what you're supposed to do. This is what we have been supposed to do for 50 years. We also have 50 years of experience that says we can't do it without help. So let's do something about it. Okay, so a lot of people talk about safety these days, and they talk about safety as if you have no memory corruption, your program is safe. Well, it isn't. You can have logic errors. You can have a perfectly typed language where I say if X where I meant if not X, and the whole thing blows. You can write programs that catches a lot of those, and I would like to see that done. Resource leaks, I mentioned. Concurrency errors, if you have many concurrent threads, processes, coroutines, you can get into major messes if you don't deal with this. Memory corruption, type errors, overflow, unanticipated conversions. It is perfectly legal in C and C++ to assign 7.9 to an integer. It may very well not give the result you expected, and if you are an expert and you expected it, you should be expert enough to know that you don't leave such code in your program for the next person to get trapped on. Timing errors, if you are doing real-time stuff, and there's a lot of real-time stuff done in C++ today, if you're supposed to finish the job, wiggling the wingtip, doing the fuel injection and such in a millisecond, and it takes a millisecond and a half, well, that's not safe anymore. Or if you press the brake, it doesn't actually do anything for a while. That is very unsafe. So the point here is not that these things are unimportant. It is that there are many kinds of safety, and I would like to address them all eventually, and I won't get overly fussed by my main concern, which is type safety and resource safety. Okay, there's many. Oh yeah, termination errors. There's people that says, well, if a program terminates, it's safe because it couldn't do anything bad. I know a lot of programs that mustn't just terminate. They can give control over to another processor. They can write a log message and get out of there or something like that. But just dying in the middle of something is just not good in many areas. If you think it is, Linus Torvald expressed his opinion on that topic much more vocally than I will ever be willing to do. So this is another kind of errors. Anyway, so I have a strategy here. I had it for a while. It's not complete. We're not there yet, but it's a cocktail of techniques, not a miracle cure. If you want a simple, clear answer, well, you're not going to get it. L.M. Mencken in the US said, for every question there is a simple, clear and incorrect answer, and we don't want those. I would like static analysis to verify that no unsafe code is executed. And if you've done anything to do with static analysis, compile time analysis and such, you know that that doesn't scale for languages like C++ or C or just about any other language that can do lots of stuff. So we need rules for using the language so that we don't get into the problems that cannot be handled by static analysis. In other words, we want coding rules to simplify the code so that we can do industrial scale static analysis. I would like to do, actually we have done, analysis of million-line programs, and that only works if the static analysis is local. Global static analysis are unenforceable. Some of the best techniques are sort of cubed algorithms or worse. You don't do that on a million-line program. And then finally, the coding rules get too complicated unless you support them by libraries so that you don't have to spend most of your time into the messy corners that are hard to write, hard to get correct, hard to verify. So that's the strategy here. The way I think about it is the way they were dealing with nasty illnesses a few years ago. They figured out if they gave one bug if they gave one medicine, one drug to a bug, the bug would evolve its way out of the trap. Okay, try the two. It is now harder to evolve out of that fast enough. And in many cases, if you attacked a disease with three different approaches, they actually died. They couldn't evolve fast enough out of it. And that's sort of inspiration to this approach here. We are attacking by three angles. Each of those has proven over the years not to scale. If you try and write perfect C++ with libraries only, there's things you just can't do. If you try coding rules, nobody likes coding rules, and anyway they can't follow them. If you try static analysis on its own, it doesn't scale. But the combination seems to work to some scale. So basically, we are going after type and resource safety as I defined it, and we have to remember that safety and security is not the same as type safety. Some people, especially in web discussions, forget about this little thing and they just say safety, safety, safety without being specific about what they're doing. Quite often they mean security. They want to stop nasty people, states, criminals to break in. Well, that's not, the type safety can help, but the whole thing is you attack the whole system. You break in the weakest spot you can find. Look, if I can break into your house and steal your computer, I probably wouldn't bother with anything to do with type safety. I've got all your bits. Okay, the Bell Labs security course started with a course in lockpicking because, well, why bother with the complicated stuff if the simple stuff works? Phishing, SQL injection, resource exhaustion, and forcing timing overruns all works beautifully. You explore the system weaknesses. And so what we have to do here for the type areas is we have to make sure that what is legal is not the same that what's safe, reasonable, efficient, and maintainable, because we still want all of those things, and we can't write every piece of code that the language manual allows. We have to protect against a variety of security issues, and we have to avoid certain parts of the language. I would like type and resource safety to be the default, so that you had to sort of take the safety off before you do nasty things. I'm not sure if I can get there, but that's the ideal. And the ideal is still that you can take the safety off. there are things that you really can't do if you want to validate, guarantee safety. Okay, I'm sticking in an FPGA or a new model GPU. How do you validate that that code that's running over there is safe? Basically, you can't. So you have to be able to take the safety catch off sometimes. So we started some years ago, me and quite a few others from different organizations, to build something called the C++ Core Guidelines, which was trying to get something where you could voluntarily opt into part of the system and eventually squeeze the areas of unsafety, uncertainty into smaller bits of your code. And so that's the approach that I'm taking now to try and get guaranteed safety. But this has been tried. You can download the rules. You can get rules checkers in Clang Tidy and especially Visual Studio. So this has been tried at scale without full verification. So this is not new. And yes, basically what I would like and what I can do is I can write type and resource safe C++ today. No leaks, no memory corruption, no garbage collector, no limitations of what can be expressed, no performance degradation, still ISO C++. I don't want to design another language. It's just too much hard work for too long. It's fun if you do it as a hobby, which seems to be what a lot of people are doing, but no. And the tool enforcement is coming. It's not quite there yet. And you can't actually write everything the way you did today. If you want safer code, if you want better performing code than we did 10 years ago, you actually have to use some new facilities, new techniques. Okay, and so I'm not covering all of these kind of interesting things in this talk. There's a logic areas, performance bugs and such. The core guidelines actually attack some of those, but I'm talking about the type and resource safety here. The fundamental ideas are really quite fundamental. Express things directly in code. If things aren't expressed directly in code, how can I, as a human reader or as a static analyzer or even a dynamic analyzer, check it? Because I don't know what it is you're really doing. If I know that the ideas are there, I can do some checking. Like if I know it is a matrix and it's supposed to follow matrix rules, I can do some checking. If it is a set of pointers and allocations and such, there's nothing much I can do because I don't know what you mean. And don't waste time and space. This is C++. We're supposed to beat just about everything in time and space, so we can't solve the problems by getting 2, 5, or 10 times slower. And I mean, there are places where it's perfectly reasonable to be 70 times slower. Python proves that, and it's a very useful language. But you know, part of the reason it does that well is it calls C++ for doing the heavy lifting, and we can't just call somebody else to do the heavy lifting. So don't waste time or space. And if there's messes, and there will be, encapsulate them rather than spreading them through the code. The thing I don't like to see is interfaces based on pointers where the semantics are unknown. Do I delete it? Do I not delete it? How many elements have we got? Spreading those out in the code means that I can't check it anymore. I can't understand it anymore. So we have to encapsulate that kind of stuff when we need it. And to go beyond the current core guidelines, which is what I'm talking about today, is that if we cannot, by local static analysis, prove a construct safe, we'll ban it. There has to be tools that can do that. We shouldn't do it for all code. We can't do it for all code because, well, there are billions of lines of old code, and you'll see that just about every significant program in C++ will break when you apply this to it. And that's fine, because we want something that we haven't had before, except for some very few places. It starts looking very much like high reliability code in embedded systems and such. And rules should help, not hinder. That is, a lot of people have designed guidelines and rules that basically says don't do that, don't do that, don't do that, and you get a list of just about anything that you shouldn't do. I would like the rules to be formulated in terms of, if they say don't do that, then you say instead do this. And I much prefer rules that says do this. We have to help, not just get in the way. And we don't want non-essential restrictions on coding style. If something is, in my opinion, ugly and wasteful, but it doesn't matter to you, I'm not going to make a rule against it. I may recommend against it if I consider it wasteful, but just because I think something is ugly doesn't mean I go and ban it. There's so many guidelines that says how many spaces or tabs do you use, how do you use your identifiers and such. Basically, that is not fundamental, and so we don't go there. We have a whole list in the core guidelines that says non-rules, which is, no, we haven't decided not to ban this or have an opinion on that. Okay, so we start with a high-level set of rules, a philosophy, because for rules to make sense, they have to fit into a sort of an intellectual framework. If if it's just a bunch of rules, how do we know which rules to include, which rules to exclude, which rules we actually need? We need to build up this framework. This is one place where the core guidelines differs from most sets of rules, which are just sets of rules. This is actually has a philosophy that's not that different from that of C++, of course, but still. Express ideas directly in code, write an ISO, standard C++. Well, sometimes, of course, you have to go to assembler or something like that, but that should be encapsulated, said that before. Express intent, so that analyzers and humans can understand what you're saying. The ideal is statically type safe, but sometimes you actually have to do some checking at compile time. So if you can't check at compile time, it should be possible to check at runtime. This is what's wrong with a pointer. A pointer, in the simple thing, points to 0 or more objects, and you don't know how many they are. So you can't even check. We have to make sure that such things don't exist in the program, because they're not just statically uncheckable, they're uncheckable. The information is not there to do the check. I mean, yes, a human can go in and try and trace it all the way back to the definition and such, but any of you who's looked at complexity knows that that's a halting problem. In general, you can't do it, and in practice it's just too difficult. Catch runtime errors early, don't waste resources, don't waste time and space again. I don't want to reinvent Java or any equivalent to that. People have already done that. It works in certain areas. They're not the areas I'm mostly interested in. And use libraries when you can, because if I can get somebody else to write the code for me and test it, I'll take that. And then you have to have the low-level rules. If you look at these rules, they're philosophical. You can't build a program to check them, at least not to any completeness. You have to get to the next level where we can get enforceable rules. In other words, that's the path through the the forest, the path through the mess that we can follow. And so we can provide enforcement, some complete, some heuristics. For the type checking, we would like them to be complete, but for some of the other rules, heuristics are useful and necessary. And so the rules are, the low-level rules are neither minimum nor orthogonal. They don't have to be, they just have to be into the framework, and they should be something that checkers can deal with. And examples like a pointer designates at 0 or more objects. There's a rule that breaks just about any C and C++ program. But you can do it. I'm not going to ban anything without giving an alternative. That's what I said before, and I mean it. If you want to have an array of something, there's span, there's vector, they can be checked, they have the information necessary, and they can do things as well as pointers plus sizes as efficiently and as elegantly. Prefer initialization to assignment in constructors. That's a rule. I, in general, guarantee initialization. And all, yeah, there it is, ES20, always initialize an object. You can be more clever than that. You can have uninitialized objects and then sooner or later assign to it or something. But how do you know you actually did that? You need a fairly clever program to do it. And anyway, there are types where assignment doesn't work unless there was initialization. So we have the simple rule there. The way we go about working on these rules is what I refer to as a subset of a superset. If you just subset the language, you will very soon find that you absolutely need some of the things you want to ban. The classical example is the pointer again. I mean, that is one of the major sources of bugs in C++ programs, so you have to ban pointers that's just points and then use them for subscripting. But so we must ban that. So the way we solve this problem is first we extend the language to a more ideal language. We add span, which we did. Span, the standard, came from this work. And now with span, we can now avoid pointers to many elements because we have an abstraction that deals specifically with that. And so the idea is you expand the language to an ideal for a particular, in general or more likely for a particular application domain. And then we subset, and we can subset very drastically. We can subset a lot of stuff away. Pointers to many elements, unions, we have variants, casting. I got a ban on casts into the coding rules for the flight software for the Joint Strike Fighter. It works. You don't in modern C++ need many casts. They are code smell. So anyway, superset, then subset, not the other way around. Everybody comes and says, let's just find a safe subset of C++. You can't if you still want to express what C++ was designed to express. Try writing a memory manager in a meaningful subset of C++, a process scheduler, even a good vector. You can't by simple subsetting. You have to do something else. So what we want is C++ on steroids, not some fairly useless subset. We have lots of languages that are good for where that is acceptable. So let's use them. But let's not try and modify C++ to be one of them. Oops. What was that? Huh? went out of. Okay, so there's the argument that some rules depend on libraries because we have added them. There are two libraries we use a lot, the standard library and what's called GSL, the Guideline Support Library. The Guideline Support Library is a very small library which we want to put out of business by making it standard. And this has happened. Like span has become standard span, but for this purpose we need all of those range checks to be guaranteed by some version of the standard. That has not happened yet. I want to be able to pull a switch on every C++ implementation that says, okay, now you have range checking. If you violate a range check, you get your predetermined error handling, which can be either termination, exceptions, which is my favorite, or nothing, which is you're back in the old world where you can make mistakes. Okay, static analysis. We rely a lot on static analysis, and static analysis must be both type analysis and flow analysis. You need both to be able to do what we are talking about here. And to scale, it must be local. It is just too expensive, too difficult to do static analysis on million-line programs, especially if they're separately compiled. But even if they weren't, you would run out of time in the compiler for doing that kind of stuff. It has to be local. Also, if somebody still thinks they can do it, think about dynamic linking. This is not a static thing. You can't do it. It has to be local. And we've worked on that for a long time. The basic idea is we can classify a thing as safe, not safe, and not sure. And what we want for this kind of work with type and resource safety is guaranteed safe or call a human to fix it somehow or other. The human can either fix it or declare it trusted or something like that. But if you're undecided, you can call a human. It's not all mechanical. Humans are actually very useful. Sometimes the type theorists don't seem to see that point. We're not out of business yet to AI or whatever. Okay, so every object is accessed according to the type at which it is defined. Start by initializing all the objects. Okay, that's fine. These numbers in the blue here are rules that are currently in the core guidelines and checked by some of the checkers. And they have names, they have numbers and names. ES, expressions and statements, number 20 rule. And the rules have numbers so that you can refer to them from software. They have names so that humans can read them. If you look them up, you'll find there's always an explanation, a rationale, an example, and if it bans something, it tells you what to do instead. And yes, there's probably one or two places where that's not true, in which case report a bug and we'll fix it. I mean, this is real software, so there will be things that are incomplete and bugs for now. Okay, fine. Always initialize an object. Even that we can't really do. The first example here, F, no, it's not good enough. It's uninitialized, and then you assign to it. We could be clever, but we shouldn't. We should just initialize it. And we should encourage people to initialize things with a meaningful value. There are languages and suggestions that says just initialize everything to 0. 0 is the most likely value to be not quite right and not caught. If you are going to default initialize to anything, you have to initialize to something horrid. 01010101 was something I used for a while. And then will force people to actually give real meaningful values. So initialize to a meaningful value. There's another rule that says that. But there is one case where we don't want to initialize, and that's things like an input buffer. If I'm going to read a megabyte, I don't want to first zero initialize the megabyte and then read into it, because now I've doubled the cost of the transmission. I used to work in finance for a while. You just don't do such things. Furthermore, yes, you could say it comes out of the disk, it has been zero initialized. No, you don't want allocations all the time. It's sitting there being recycled. So you have to be careful. So there has to be some kind of exceptions to the rules, and I do not quite know how to express this. There's several ways. You could have an uninitialized value that you could use for an initializer that would tell static analyzers and humans to be careful. You could have trusted code or things like that. But we need something, otherwise we're actually breaking C++'s utility in areas where it matters. There are places where, well, at least microseconds matters. Counting nanoseconds are sometimes a very useful thing to do. So every object is properly constructed and destroyed. Don't read any, leak any resources. In other words, RAII throughout and enforce it. Don't have manually dealt with resources. There's been some research over on the MISRA end of analysis that shows that people really don't know how to unlock their locks, and that has been been proven in many cases over the years. If you see new, there's a good chance that somebody forgot to delete somewhere. If you see a lock somewhere, there's a good chance somebody forgot an unlock. I mean the function, not the object. So RAII throughout, there's a bunch of rules for dealing with this, and notice these rules that I'm talking about now are verifiable. You can run a fairly simple piece of code over a simple analyzer over the code and catch a lot of them. Okay, no dangling pointers. Now we're starting to get into the difficult stuff. Every pointer either points to an object or the null pointer. And when I say pointer, I mean anything that points. Pointers, references, containers of pointers, smart pointers, lambda captures, the works. And a lot of it has been done. I thought I caught the analyzer guys once by thinking about a really sneaky way of binding a local variable to a lambda and then returning the lambda and then using it later. They caught me. Good. Okay, so there's a lot of details for turning these rules into reality, but the rules themselves are simple. Now we're talking about pointers, and you can, by good engineering, turn this into something that applies to everything that points. Okay, we have to deal with this. So here is a naive piece of code that looks innocent and is very much not okay. There's a function, f of x star, it deletes the p. There's another function, imagine it over on a different part of a program, separately compiled, developed on the other end of the world or something like that. So it doesn't fit nicely in this kind of single slide. But what it does is it allocates an x, it calls f with that x, and then it goes and uses that pointer again, but the pointer was destroyed up in the in f. In other words, we have a dangling pointer and we use the dangling pointer. This must not happen, because if this can happen, if use writes, I'm writing into some data that's some part of memory that's not mine. It may be yours because it got allocated and you used it for your precious data, and now I come and write to it. It's not acceptable. Similarly, I can read out something and it may be garbage. One of the nasty things about reading a dangling pointer is that a lot of the time it works. If you just read it quickly enough before it gets reallocated, it works. So you test your code, you ship it, you wait a week, and now it starts breaking. I don't like catching such bugs. I don't want to have to debug for that. I want it caught up front. And so this is my picture of a nightmare, because this is the nightmare scenario that has to be dealt with. So we must eliminate it. Otherwise, everything goes haywire. So we eliminate it by a set of rules. As usual, the drug cocktail idea, we will deal with it. First of all, assume all raw pointers are non-owners. That is, you have to somehow mark that something is an owner of an object, meaning you have to delete it. And so if deleted is a destructor that unlocks the things and such, it all takes care of that. And you have to stop pointers from escaping out of the scope of the thing they point to. Okay, so a pointer can be returned from a scope if and only if it was passed into the scope. Hey, if it was given to me by you, it must be good because you follow the rules too. And therefore it's a valid pointer that comes into me, and it's a valid pointer when it goes out again. I can't delete it because I don't own it. If it points to an external object, like it was returned by new, or it points to a static, I can return it, but I cannot return it if it is a local variable. And of course, if I call down, the same rule works again recursively. My callers can't return it to me. But it does mean that I can pass a pointer, say a pair of iterators, to a caller, and it's perfectly good. And they don't need to do any extra checking, they just run. They know those pointers are valid. What they can't do is delete them. That's not allowed. And so ownership and invalidation rules should guarantee, and does guarantee, that pointers point to an object or are the null pointer. So here's an example here. P is the result of new. I have made an alias with Q. I've deleted P. I'm using Q. It's not okay. Static analysis can catch it. Returning Q is not okay because, well, it had already been deleted under the name of P. This, by the way, is the proof that you need flow analysis in your static analysis. That's particularly painful for me because I don't have a flow analyzer that fits into my framework, but other people do. So that's good. I'm not the only one doing this. And escaping pointers here, I can try and return those pointers. The pointer to local, no. Everything else fine. But there is a problem. If I return the new as I did there, how on earth do I know that I must delete that one and not delete the pointer to global that was passed there, or the one that came in there? We have to be able to distinguish between things we have to destroy, we have to delete, and things we mustn't. That's such thing. So don't dereference an invalid pointer. We can do that. I've talked about dangling pointers. I'm now going to talk about invalidation. That is the case where a pointer is made not valid anymore. So an owner is somebody who is responsible for invoking a destructor. It can be a scope, it can be an object, and something holding an owner is an owner, and new returns an owner. And there actually is an annotation that you can put into the code called owner. So if I want to return something that was given to me by new, I can say owner of T, T star, and that's the owner. And if I don't do that, well, it can't get deleted. That's fine. That's my problem. I'll show some examples about that. It can be used as static analysis, and even if you don't have a static analyzer, it actually is very useful in writing your code, because then you know what you're doing. It's easier to debug, it's easier to look at. And the definition of owner of T is just type name T using owner of T. So owner of int star really comes out of the other end of the compiler as an int star, which means that we have ABI compatibility. We can pass it to C. If C doesn't follow the rules, well, that's something else. But we haven't broken every C-style interface in the universe. And that's important. I thought of having owner a real type way back, like 15 years, when thinking about couldn't something like unique pointer do this job? And you can't pass a unique pointer through a T-star interface. That's unfortunately, but this can do it. So keep static analysis local. Use owner annotations for when you have to. Basically, let's see here. I delete something that's a non-owner. Well, it's if I'm not the owner, I can't delete it. Okay, so that get caught. I can pass a non-owner to pass an owner to a non-owner. That doesn't work because I throw useful information away. We can simplify analysis, the human analysis, by having the static analyzer make sure that it only triggers when it actually gets out of the function. But that's an optimization. Basically, you cannot assign new to a plain int star. You can loosen that a bit without actually violating anything, but because one of the things we do with static analysis is try to minimize the false positives. If you get a false positives, you either ignore them or you suppress them, and so it doesn't work anymore. It has to be practical. It's also an engineering job. It is not pure math. Okay, ownership here. I have an owner and I delete it. That's fine. As a matter of fact, if I'm an owner and I don't delete it, then I must pass it to somebody else. Ownership doesn't just disappear. It can't, because then it would be a leak, and that's against the ground rules. It was up in the philosophy section. And there you have a user, owner, and I pass it up to the owner. And since it's been passed to the owner, it must have been deleted. Therefore, we know that that star P is bad. We just gave away the ownership with the obligation to delete it. So don't do that. And the analyzer can do it. Prefer ownership abstractions. If you try and annotate a large program with owner, you will soon find two things. It's a right royal pain in the neck, and you don't want to do it. And two, you get it wrong. There are massive annotation systems out there, and the more annotations you get, the more erroneous annotations you get, and you get the bugs in one remote from the code, you get it in the annotations for what is supposed to be right. So we don't do that if we can help it. Use ownership abstractions that has the owner inside it and has the semantics of it in their constructors, destructors, vector, map, unique pointer, file streams, JThread, you name it. Owner annotations are for implementation of these abstractions and to avoid ABI breaks when that's important, like for your operating system that are littered with that kind of interfaces. It's most unfortunate, but it's true. I would rather have had an encapsulated version, but I don't have one yet. Okay, so here's an example of how to use an ownership abstraction. A vector is usually 3 pointers: the allocated space, the end of use space, and the end of allocated space. The first is an owner. It's the obligation of LM to delete things when they're finished. Space and end are just pointers, and there's some manipulation of getting them right inside here. This is a kind of delicate work that's sort of tricky, and we have to do something about it. Maybe we can verify it, maybe it has to be trusted code. Invalidation: any operation that may reallocate the elements of a container elevates all operations on it. In other words, say I give you a vector, and then one of us do a pushback so that they get reallocated. If we still each have a pointer to it, only one of us is going to get it right. So if he does the pushback, now my pointer points into the wrong memory. Not allowed. So we have invalidate the rule, and anything that holds a pointer is a container here. Classes, lambdas, that was what caught me. They had thought of this. One of the interesting things is that if you put a pointer over on a thread and you keep a thread as a container, all of this rolls out and works for threads too. So it's part of the concurrency part of the core guidelines, which are otherwise not that complete, but it's interesting. And so, yes, here's the concrete example. G calls F does a pushback, but G has retained a pointer and try and use it after F has reallocated everything in it. This is real. I have seen this in real code with vector. Somebody passes a vector over to another thread. The other thread needs more space, reallocates the vector. The original, holding a pointer, which they shouldn't have done, gets clobbers the system. Okay, we can catch this. This is very easy. The first order of this is that if you call a non-const function, you must assume it invalidates, so you can't do it. And that's only a problem if you held a pointer. The real villain here is that v.begin, but yeah. Currently does that. I think we might need a not invalidating annotation. You can annotate a function says, I know I'm not a non-const, but I'm not invalidating. This is not just a promise, because we can validate it. That is, when we see the definition of that operation, like vector swap or vector operator subscript, we can validate that it doesn't invalidate. Ta-da! And so this is the best kind of annotation. It just speeds up the analysis, and it makes sure that you can do separate compilation of things. Okay, don't use pointers to pointers or references to pointers. It's actually one of the old rules in no, it's not an old rule, it's a suggested new rule, because it does invalidation quite often, and it is a well-known source of bug problems from way back in the 70s. So deal with it. Validation here, more validation problems. It's actually subtle. Consider vector insert the front of the vector into the beginning of a vector. Poor implementation would reallocate and then copy into the wrong place. It so happens that the standard is written very carefully, so it mustn't do that. So it doesn't. The first is okay. It's guaranteed to work. The second, vector insert a range, that's not a problem. The range doesn't point into the old data, so no problem. But the third insert there, insert a range, which is basically a sub-range of what I'm trying to insert in into the vector. That is a likely disaster, and it will be caught by the it is caught by the invalidation rules. You can't do it if you're running the core guidelines at full crank, which you can in Visual Studio. If it's lists, there's no problem. Lists don't reallocate, so poof, the problem has gone again. I mean, you can see a lot of these problems are fundamentally very hard, but if you deal with them with a well-chosen approach from different angles, invalidation is static analysis and such, you can do a lot. Oh, by the way, I tried that vec insert or vec begin, vec end, and I ran it again and again, and you know it all worked. Because I did not reallocate the old memory in between the calls. This is one of these nasty bugs that a test program, as I wrote, I put all of that in 3 or 4 times so that the vector grew and grew. Everything worked perfectly. Unit tests doesn't catch this kind of stuff easily. You actually have to allocate, deallocate, allocate something that happens to reallocate what you did before, and go and scramble it somehow before you notice it is. So this is an example of a particularly nasty bug that is really hard to catch with anything that is not static analysis. You could imagine it testing because vectors are contiguous, so you can check whether the argument points into it and such. You could do runtime check there. It's not what we do, but you can attack it in a variety of ways. One of the things that worries me a lot is that we don't have a general widely used abstraction of a memory pool. And one of the things that that gives C++ a lot of its power is the ability to take chunks of memory and use them in some particularly useful way. It can be a tree, it can be a map, it can be a vector. I own this memory and I deal with it. That's a memory pool of some sort. And you can build your own memory pools, and people do. They are there by the tens of thousands. And so how do you handle this kind of control with that? And I don't have a general answer. I have a particular answer for what I'm doing. Either don't deallocate memories. So if you put memory into a container, never delete it again. There's lots and lots of data structures that just grow. So they're not a problem. And the other thing is that you could do invalidation. That can be drastic. Or finally, you can separate ownership from pointing. And so you allocate over here. The users never deallocate without not invalidating. And so you need to do something here. Here is the example of how you get into trouble. I have a tree node, which I carefully use the tree nodes to be unique pointers, so everything's careful. Works nicely unless you have a loop. That leaks. And I said I don't like leaks. Leaks has to be caught. So this thing will be caught. Because it is fairly easy for a static type analyzer to see that you can create loops out of that data structure there. So we can catch it. So what do we do about catching it? And you could either not delete, or you could do something like this. The tree owns all the nodes, and the nodes just point back into the data structure that the tree uses. That is very much the way vector and the standard library things do. And if you measure the size there, it's about the same size. Because once you allocate something over on the free store, there has to be memory there, whereas the vector of unique pointers to tree nodes or vectors to even to pointers to tree nodes doesn't take up more space than it did before. This is not a general solution. I mentioned that this class of problems I'm not too happy with. I can solve a lot of the cases, and I can solve a lot of the cases up to really good performance, but I can't give you a general algorithm that says this works for everything. So, sorry about that. We can deal a fair bit. This is a problem. I told you this was work in progress. If you have good ideas, I'd like to hear about them. Some runtime checks are unavoidable. We have null pointers, we have range errors. So we do that. And by the way, that means that the things like null pointer and span has to do the checks and report errors. The standards currently doesn't guarantee it for span, which is a very great pity. It was proposed with guaranteed checking, and they don't have a null pointer. So there's a span, and you can do, once you pass the information, you can write really good code. It's not okay to write into the pointer of 7, because we cannot prove if this is right or wrong. We can do it for span because we can runtime check that one. And anyway, we don't need to do any range checking because we know how many elements there are, so we do a range for loop. So I have seen significant pieces of code speeding up as people changed from pointer, comma, size to span, because now they could then write their code in terms of range for loops, which are faster than anything that is actually range checked. Good. And null pointer problems, you have to check it. A null pointer check is done. It's a type that throws an exception if you try and assign a null pointer to it. I was amused that when I looked up null pointer problem and null reference problem, all the pictures that came up was from Java. So I couldn't resist using that one. This was the result of a Google search for the words I wanted to of the bugs I wanted to remove. So there's a not null. Once you have not null, you can actually see that the test of not null inside the function is redundant, and you could eventually remove it, even mechanically. Whereas usually when I pass a char star, a t star, I don't actually know whether I'm supposed to check it for null or not. Look out in the manual. You can't remember them all. So you have to look up and then you forget. That's good. Not null use. It also means that for static analysis you can start removing the checks down the line of calls, because you've already proven here that it is not null, and then you can actually avoid the checks further down. It's a bit more complicated to do from a static analysis code generation point of view, but it has the potential for speeding things up. That's always good. We have to deal with one past the end pointers. That's nasty because there's no single no past the end. Every iterator type has one, and they're different. So that's a nightmare for static analyzer writers, but, well, we can do something. I suggest that there should be a GSL not end that is the standard way of calling a not at end check, because everybody has one. They're just different. But we don't have one of those yet. Work in progress. Low-level code, we have to be able to do it. I suggest that there has to be something we can call trusted, unvalidated, something like that. This is necessary. What we do now is we use profiles. A profile is a set of checks to be executed by the static analyzer. And that means that you can specify something like the memory profile or the range profile, and you get a coherent set of tests that are being applied to the the program. If you have to pick out of a list of 60 or 80 tests, you're not going to get a consistent answer. You're not going to make mistakes. You're going to forget some check or other. So we group them. The people that are doing the static analysis and such, they're experts. They group them into something that fits the general philosophy of the whole thing. And then you can call them, so we can do that. Concurrency. There's lots of concurrency rules, not anywhere near as many as there should be, because C++ has to serve the operating system and the systems world, where we have the thread and lock model of concurrency, which is messy. And so some of these rules get messier than you could imagine, but it goes. JThread is a joining thread, it obeys RAII. It's C++ 20. We had one in the core guidelines before that, the rules. And there's a nice talk by Mike Wong in C++ Con 20 about Mistra C++ that is addressing some of these concurrency rules. Notice that think of a thread as of a scope container. That means that we know when the pointers in and out of it are invalidated, and so all the invalidation rules work, and we can catch sort of invalidations, leaks, dangling pointers across thread boundaries without any extra cost, because it's just the rule. And so why don't we enforce through language rules? Because the language is too complicated. We have lots of code, and there's different definitions of safety. Furthermore, with billions of lines of code, we have to go for gradual adoption. We can't just say stop the world and rewrite these billion lines of code. So what we do is to adopt partial solutions, and we work on that. And that gives the problems, by the way, of what happens if my safe piece of code, for some definition of safe, calls unsafe code, or if unsafe code calls my piece of safe code. We don't quite know about that. We're working on it. Gabby Dos Reis and I have a paper in the standard repository from last year. You can look it up and find it. I'm sure I have a reference here somewhere. And so back to the point I was trying to make in the beginning. There are many notions of safety. This talk addresses one of them. And we should just remember that that's not the whole answer. And why the core guidelines? Arbitrary C and C++ code is too complex for static analysis. Arbitrary C++ forces us to deal with too low-level abstraction levels, so we need libraries. And we care about performance, so we can't just throw in a lot of runtime checks. Core guidelines, because we're trying for a coherent set of rules, not just a set of rules. There are lots of people have 50 or 100 rules, but we can't actually summarize what they do. Here we can summarize what they do. And there's the strategy again, the drug cocktail, static analysis, coding rules, libraries, and there's a whole bunch of references, including links to the core guidelines over on GitHub, where you can find them. The best implementation is in Visual Studio currently, partly because my friend Gabby Dos Reis works there, and he does lots of good stuff. And based on our old stuff, I have some talks, some papers also there. Herb Sutter has a nice paper, the one Lifetime Safety Preventing Common Dangling, which is attacking the details of the dangling pointer problem. And most of it is deployed today. Clang Tidy is trying to catch up. I hope they will soon. I know the JetBrains people are working on core guidelines enforcement. I hope they catch up soon. This is not where a race where you want to win. It's a race where you want everybody to get to the finish line as soon as possible. Boom, boom, boom. Yeah, there's my call to action from a couple of weeks ago. And the paper I mentioned, Design Alternatives for Type and Resource Safe C++. No, that's the, yeah, that's the one. That's the one that discusses the different kinds of safety and how you get into problems. Once you get some kind of safety, how you interact with other kinds of safety, which is problems that you will get into whether you are in separate languages or same language or dialects. Languages don't stand alone. They work in a group of languages in a program. Okay, questions? Okay, there's a mic coming.
Okay, questions?
Hi. Well, thank you very much for your talk. I have the opinion that ensuring the safety of a program is as much a technical issue as it is a human one. It has some human factor in terms of convincing people that they should use the tools that are at our disposal to prevent those problems, etc. And then you are aware of these like safety wars raging on the internet about, and there are languages that are advertised as safe by default, like you have to opt out of safety rules, etc. Okay, C++ is not doing that. I don't know if it is a cultural thing because programmers basically want to have absolute freedom, etc. Do you think, or what is your opinion about the standard being a little more assertive in terms of basically enforcing that some of these techniques are on by default, not only available?
I am proposing that the standard supports these. I may suggest that it's the default, but I think if I did, I would probably lose because there's far too much code that doesn't that doesn't fit, and you have to move in there gradually. I would actually say, and I said it on the slide, that you should take the safety catch off to do other things. I think I'll lose that battle. But the fact is that there should be a safety catch. And I think a lot of the talk about safety now and safety by default and such are somewhat naive. New languages are new and shiny and small and claim to solve all the problems. In my opinion, they never do. So Java's main argument for over C++ was that it was safe and portable and fast and small. Well, for starters, it grew by a factor of 3, as I predicted at the time. Secondly, it wasn't safe. And thirdly, well, I've forgotten. But anyway, it wasn't fast. It was good enough for huge areas. That's fine. I mean, maybe there are people who want their language to rule the world unconditionally and alone, and I'm sure not one of them. That would be stupid. So people want a simpler solution. And I think the main problem is the fact that there's many kinds of safety, like the performance safety, the memory leaks, things like that they don't address. And all the safe languages have ways of taking the safety catch off. And once you have the safety catch off or on, you have to know where it is. And yes, they say it's only very small pieces of code that are not safe, but experience shows that when things hit the masses, sloppiness becomes much more common. And so you will see a lot of safe code with the safety catch off, because that's what programmers do when they're in a real hurry in the middle of nowhere and the boss breathing down their neck. And there's a lot of complicated data structures, complicated data that just doesn't fit those models. Yes, it should be encapsulated. Yes, it should be encapsulated here. But by default, I'm not so sure. In other words, it's a stronger statement than that. I think it'll be more common to have unsafe code in the safe languages, and it'll become less common in C++, but I'm not into absolutes. I would like to see the default, as you suggested, to be safe. I think I'll lose that battle. For good reasons. People aren't stupid.
Thank you for the presentation. In some page, you mentioned MATLAB C. I think that kind of rule are in contradiction with core guideline, or some point at least. Do you recommend that?
MISRA C is in contradiction with the core guidelines in several areas, because they work strictly on subsetting and they won't rely on libraries, which means that they have to prohibit necessary things. That doesn't mean they are useless, but it means that there is a contradiction and there is a clash, and people are trying to deal with it. There are C++ core guidelines people on the MISRA groups. And we are getting some of the MISRA concurrency rules into core guidelines. I'm reviewing them, not quite as we speak, but certainly in these weeks. So I didn't say it was useless. But I think we can do better, but that's, of course, I would say that.
Wonderful talk. Thank you very much, Bjarne. Talking about safety rules and good rules, you mentioned the importance of different tools. And I think that the latest fancy tools being in use nowadays include Code Whisperer, Tab9, GitHub Copilot, and all these things. My question is just simply, what do you think about all of that?
I think there's an absolutely confusing set of rules and tools, and that people say something like this is complicated or C++ is complicated, and then I look at the tool chains in major corporations and my mind boggles. Yes, I'm adding one to the problem, but I don't see any alternative. There is this thing I call the N+1 problem. You have N problems, you come up with a solution to it all, now you have N+1 problems. Yes. I don't see any alternative for these kind of safety concerns except a tool approach. But this is a combined approach, because I don't see any of the single approaches to actually do the job.
Mr. Stroustrup. I didn't hear about the GSL libraries before. Are GSL libraries enforcement rules applied in compile time or in runtime time?
You're speaking very soft.
Sorry, I know it.
I'm having trouble.
I know it. Are GSL libraries enforcement rules applied in compile time or runtime? In other words, the use of GSL penalizing time can be used in critical real-time processes.
GSL is mostly runtime. So span, GSL span, is probably the most successful part of the core guidelines. There's only about 11 or 12 things in it, and we want to put it out of business. But not null is runtime, span is runtime. We have some very primitive asserts that would be runtime. We had hoped to put them out of business with a good concept, good contract system, but that went down the drain, unfortunately, and now we're stuck with something that's not good enough in the GSL. We might have to revise it, but there's very few things, and some are like owner, a compile time thing, but I would say most of them are runtime, and they're very small. We don't. The last thing we wanted was to come with, this is the library for everybody, and you should build everything on top of it. We thought that was guaranteed to fail. It had to be small and easy to fit into particular places. You can use owner today. It won't even affect your linkage. You can use span today, but it requires you to take your p, n interfaces and turn them into spans. You can do that for all of the ones you own yourself. You can't do it to the ones owned by somebody else, unfortunately.
In your paper, A Call to Action, you say, and I quote, it, the NSA report, lumps C and C++ into the single category of C/C++, ignoring 30 plus years of progress. In yesterday's talk, you also say that there's a strong need for compatibility. How do you reconcile those views?
Let's see. First of all, C and C++ are not really the same. You're right, really different programs. And you need compatibility in some areas. Like if you want to call the operating system Linux or Windows, you have to pass pointers and integers. So you have to be able to do that, and I'm keen on that. I think C/C++ is intellectually sloppy if it is used by people who want to be professionals, and dishonest if it's used for advertising people, because they won't say what they really want. For compatibility in the general sense in C++, I don't want to break code unconditionally. That is, one of the strengths of C++ is that 10 or 20-year-old code can work if nobody rearranged the operating system and something like that. And that's a thing. We have tried several times to deprecate things in the standards committee, and it just gets ignored or complained about. We had a guy from Sun, when Sun was a major factor, who says if you deprecate anything, it cost us $1 billion. I think he was exaggerating, but not much. I've seen the effects of breaking compatibility over the string implementation in GCC. We're still suffering of that 12 years later. So I'm very keen on compatibility. That is, old code should run and have the same meaning as it had before. On the other hand, I'm very keen on trying to stop me and others from writing code I know is bad. And for that reason, I have to have this two-level approach. Compatibility in the language, modernization in the use of the language. And this is the safety thing fits into that pattern.
Hello, Bjarne. Yeah, you mentioned the C++ contracts feature, and I was just curious to know what happened with it, because I know it was dropped in C++ 20. But yeah, just curious to know what happened.
Well, my answer is very simple. It should have been approved for C++ 20. It was good enough, and it was much better than what they are proposing today. See, I can give a straight answer sometime. It's some things aren't that subtle.
Yeah, let's see. Perhaps a second question. Some of those attributes in C++ 11 notation that you mentioned, the trusted thing and there was other, are those meant to be parsed directly by the compiler, or are those meant to be ignored and just parsed by some static analyzer tool?
You lost me there.
So this...
Slow down, please.
These C++ attributes that you mentioned before, the trusted attribute and the not invalidate thing, are those meant to be parsed by the compiler, or just ignored at compile time and just be parsed by some static analyzer tool?
Oh, I hope that many of the rules will be part of the compiler, but I don't want compilations to be slower than they already are. We're speeding things up dramatically with modules, but let's not slow them down again. And a lot of the analysis that you do in the static analysis are really slow. As I said, O-cubed algorithms or worse. And I don't want those algorithms to be into every compilation. I want actually you to throw a switch, and that comes together with the switch we talked about there. The safety catch may actually have to be default off because it is expensive. And so you throw it before you ship, and whenever you get a bad bug in your debugging is one way I imagine it might work. But the algorithms are simply too expensive to all be put in there, especially one that are flow sensitive. But some can get in there. Like initialization rules, for instance, I think could be easily put in there, and that would be help. It would be easy to have a switch that says no raw unions, use variant, things like that.
Hi, first of all, thank you very much. And my question is, on last talk, you talked about how one of the aims for C++ is to make the language simpler. And then I was wondering if this aim to be simpler would make the language safer per se. Is simpler code safer, or is that not really a relationship?
I think on average, simpler code is safer and faster. That is, a few years ago, I started efforts to optimize by ripping out all the clever parts. Because if I couldn't understand it, there's a fair chance that the optimizer couldn't understand it. And there's no law that says that's the case, but it's often the case. And quite often I don't have to put in the clever parts again. Actually, I wrote a paper many years ago with Professor Garcia Sanchez on analyzing some concurrent systems, some flow dynamics, and we ripped out the clever stuff, and things we wanted to see how much slower it got. It got a little bit faster, just a little bit. So you can read an example right there. Thank you.
Okay, thank you very much. Master students that have to sign in the list. The list is here. Thank you everybody for attending and hope to see you soon again.